it is time to start moving. Well, actually, we're not going to be moving, but we're going to be studying moving, motion. Specifically, as we see on this slide, we're going to be looking at Newton's laws of motion. Now, remember, I talked to you about early thoughts on how motion occurs. From the time of the ancient Greeks to the medieval age, scientists believed that things tended to stop if left to themselves. Okay? They remember that tendency. Oh, it's built in. Oh, this thing wants to rise and this thing wants to fall. It has a tendency. And we find that that can mess you up if you don't think about it right. Because notice what it says in the slide. It says they tend to stop if left to themselves. This is true, but does it mean that the objects stop by themselves? Nope. Now, our scientist, Galileo, did some investigations. Now, I won't go into detail, some experiments trying to find out, do things stop by themselves? And he was able to come to some conclusions in spite of the fact that the way they timed the objects, the ball moving down that ramp, was by music. You know, they knew the tempo of the music, and so they could kind of repeat that tempo and see how far they got in the song at different things, because they didn't have any clocks to work with. So what did he figure out? He concluded that objects do not have a tendency to stop. Okay, if an object doesn't have a tendency by itself to stop, but yet, you know, if you start something rolling, unless it's on a hill, if it's on a level surface and you give it a push, it's going to stop. So, therefore, what's going on? So, here's what he came up with. In order for an object to stop, it must be affected by some outside influence. Okay? That's something that causes the object to stop. Okay, now Galileo found that what this means is when you get an object going, it wants to keep going. Okay, and so our next note says he called this property. Now the property of continuing motion. So you might want to put that there because it almost sounds like I'm talking about the middle build, but I'm not. Galileo called this property that motion wants to continue unless some force acts on it. He called that inertia. Just like there is mass in an object, there is inertia in an object. An unwillingness, if you will, to change motion. Newton had clocks that were accurate enough to start making measurements. Okay, so he extended Galileo's mostly concept studies and formulated the laws of motion. See, Galileo could get the concept, but he couldn't really figure out the details of it because he couldn't measure it. When you can start putting numbers in and getting numbers out, then you're starting to understand things. And that's what Newton was able to do. And so he came up with the 3 laws of motion. His first law is called the law of inertia. Objects at rest remain at rest. Objects in motion continue in that motion. In other words, if they're moving in this direction, they'll keep on moving that direction. They don't start going like this, whoop, by themselves. If they're stopped, they stay stopped. If they're moving, they stay moving the way they are moving. Okay, and our next note says, unless there is an unbalanced external force. That's important. An unbalanced, remember it's external, not internal. We talked about that earlier, but I'm doing that for emphasis. An unbalanced force. So basically, that's just simple. That pen is going to sit there unless I push it. Duh. Okay? You can handle that. We cannot measure inertia directly. We measure it indirectly through the mass of the object. In other words, mass and inertia are tied together. You can't have one without the other. The more massive it is, the more unwilling it is to get moving. The less massive, the easier it is to get it moving or to change its motion once it is moving. Going like this, that's going to change its motion. Remember, it keeps moving in that motion unless that unbalanced external force acts on it. All right. So, if no net force acts on an object, the object is in equilibrium. If an unbalanced force acts on an object, it's going to change its motion. Okay. It has to be a big enough force to overcome friction, we'll talk about. Okay, if I just go up to the desk and push with 1 pound of force, it doesn't move. It just doesn't move. Okay, but if I push with 50 pounds of force, then I can start moving the desk. So it does have to be big enough. Okay, now as a summary, well, first of all, let me give you this. The force can be a contact force or a field force or a combination of both. So you can be pushing on an object while gravity is pulling it. Okay, that would be a contact force and a field force together, or separately, just one of them. Okay, so what is this first law about? Here's our summary. Inertia is the tendency of all objects to have an unwillingness to change their motion. The more mass an object possesses, the more inertia it has. I like that word. Possesses. Just has all those S's in there. Okay? So, the bigger it is, the harder it is to get it moving. Once you get it moving, the harder it is to change its motion. Okay? And that's what we're talking about. Now, let's see that in some video clips. First of all, we're going to see how a large ball, a relatively large, heavy ball, wants to stand still.
Newton's first law, also referred to as the law of inertia, states that a body at rest tends to stay at rest, and one in motion will tend to stay in motion. Inertia is similarly defined as a tendency for any object to resist change in its state of motion. To demonstrate the property of inertia, a heavy iron ball is suspended by a thin string with a second length of string attached to the bottom of the ball. The amount of inertia which an object has is determined solely by its mass. The more mass, and therefore the more inertia an object has, the harder it is to change its state of motion. By applying a force to the bottom length of string in two different ways, interesting results can be obtained which illustrate this property of inertia. If the bottom string is pulled with a slow, steadily increasing force, the upper length of string is observed to break as a result. If a quick, sharply applied force is given to the bottom string, the bottom length of string breaks, leaving the upper length unaffected. To explain these results, let us consider the forces acting during the first trial. Before the force is applied, the upper length of string is initially under a tension equal to the weight of the iron ball, whereas the lower string is under no tension at all. As the gradually increasing force is applied to the lower string, the tension on every element of the suspended system increases by the same amount. Since the tension on the upper string is equal to the weight of the ball plus the applied force, It experiences a greater force than the bottom string and thus breaks first. During the second trial, the sharply applied force appeared to have no effect on the upper length of string. This can be explained in terms of the ball's inertia. The ball, being of relatively large mass and large inertia, has a strong tendency to resist any change in its motion and tends to remain in its original state of rest. As a result, the rapidly applied force does not cause the ball to move or accelerate by any appreciable amount, and the force is not transmitted to the upper string. Instead, the force is felt fully by the lower string, which consequently breaks. Newton's first law explains the type of motion to be expected in the absence of a net force. Objects will either remain at rest or travel with a uniform velocity along a straight line.
Our next demonstration answers the question, well, how long does this inertia last? Just a small fraction of a second. Now, when you get to the shattering glass, I think it's a light bulb, if you look kind of right in here, the upper right-hand quadrant, you can see one piece that kind of stays together and hangs there before it starts falling. Let's see everything.
When a water balloon is burst by a sharp instrument, the surface of the water is disturbed by the rapidly retracting balloon. However, the bulk of the water retains its original shape for a short period of time. Slowly, the force of gravity pulls the sphere of water downward. In this rather dramatic demonstration of inertia, the water at rest tends to remain at rest, even after the balloon is no longer holding it in. A second example of inertia can be observed when a bullet is fired through a glass bulb. Upon impact, the glass shatters, but the inertia of the bulb causes its pieces to remain in position for a brief instant before falling. A body's inertia is associated with its mass. This is evident when a massive concrete block is placed atop a small drinking glass. When a sledgehammer imparts a large force on the block's inertia prevents the blow from being translated to the glass below. The drinking glass remains intact as the impact force demolishes the concrete block. When the same force is applied to the glass directly, the result is altogether different.
Our next demonstration explains why you need seat belts. When you see the ketchup sloshing out, think of you sloshing through the windshield without a seat belt and the airbags and things like that. You do not understand the amount of force that's generated by getting a car moving at highway speeds. You're not going to be able to hold yourself back. No, you can't. Okay, so think of that as you enjoy the other first law clips.
A body's inertia can often be exploited for useful purposes. In this example, a metal wedge is fitted into a narrow slot on a piece of wood. The two objects are then raised above a horizontal surface. When released, they fall together, but upon impact, the wood comes to rest, while the more massive wedge continues its motion, splitting the board. Due to the large inertia of the wedge, it has a strong tendency to remain in motion. Inertia can also be applied to the age-old problem of extracting ketchup from a ketchup bottle. To demonstrate this, A ketchup bottle has been mounted horizontally to a metal cart. A funnel is positioned in the mouth of the bottle, and the bottle is partially filled with ketchup. Once the loading process is complete, the cart is propelled across a horizontal surface. As it strikes a rigid barrier, the cart comes to an abrupt stop, and the ketchup spews out of the narrow opening. The tendency of the ketchup to remain in motion drives it out of the bottle.
Okay, so hopefully you have a grasp on inertia and you're not going to let it go even if it starts dragging you along, right? Oh, Newton's second law deals with accelerated motion. It relates three quantities, force, mass, and acceleration, in this equation. F equals ma. Now, I call that the Ma law because there's Ma. Ma. Now, you look at this and you go, I don't get it. All right. Think of elementary school when you had something like this. 2 times block, and they had a square there, equals 6. Oh, that's 3. And you were basically testing on your multiplication facts. You get the idea? Guess what? That's all this is. Okay? Look at it again. Force equals mass times acceleration. Say the force is the 6 and the mass is the 2. Then what does the A have to be? 2 times what equals 6? Oh, A has to be 3. Okay? It's that easy. If you put the numbers in, 6 equals 2x. 6 equals 2 times A. The A is 3. Now, there's another way to do that. Okay? If both sides are divided by the mass, we would get the acceleration is the force over the mass. Huh? Okay. 6 equals 2 times something, which we know is 3. Let's divide both sides by 2. 6 over 2 equals 3. Take that force, 6, divide it by the mass, 2, and you get the acceleration, which is 3. It's the same thing you would do to solve it. Now, I know you know that 6 equals 2 times 3. You don't solve it. But if I had 17.842 equals 6.01349 times A, you'd have to divide that. You don't know that in your head. You get what I'm saying? So we actually end up dividing by one of them to get the other one on that side. That's what it says here. The acceleration would be the force over the mass. Okay. Now, what does that mean? If the force, what does this law mean? If the force increases on an object, and when we talk about an object, that means constant mass. The mass isn't going to change. What happens to the acceleration? Okay, this is what you really need to understand this. This is not hard, but it's very, very important. You have something on one side of an equation, something on the other side of an equation. If I increase over here, what's going to happen over there to keep it equal? Does it have to go up or does it go down? Well, suppose one side increased, the other side decreased. Would they stay equal? No. If one side of the equation increases, the other side has to increase. Okay, so if I have an object, the mass stays constant, and I increase the force on it, it's going to do what? Accelerate more. Our note says acceleration increases. Now, this is a direct relationship. A direct relationship. This one goes up, that one same direction, same direction. If the force decreases, the acceleration decreases. Let's apply that. Force increases, acceleration increases. There we see it in the equation. Now let's see it in real life. Okay? If you take a light car and you put a really, really, really powerful engine in it, it goes really, really, really fast. If you take that same light car and you put a much smaller engine in it with less force, then the acceleration is a lot less. Okay? Was that hard? No. What if we change something else? If the mass increases, but the force stays the same, what's going to happen here? Okay, now remember, 6 equals 2 times 3. Force equals mass times acceleration. What happens if the mass goes up from 2 to 3? Then the acceleration is going to go from 3 down to 2. If one goes up on the same side, what does the other one have to do? Go down. I don't get that. Doesn't it make sense? If on this side of the equation you increase, then on the other side you're going to increase to balance it. On the same side, if I have two people on a seesaw and one grabs onto something and has more mass, the other one's got to get rid of some mass if they're going to stay balanced with the other side. One gets bigger, the other one has to get smaller. Or mathematically, I had the force was 6, the mass was 2, the acceleration was 3. 2 times 3. If the 2 goes up to a 3, the 3 has to go down to a 2. Or, if it went up to 4, it'd be 1.5. 5, 1 1/5. So as the mass keeps increasing, 6, the acceleration is down to 1. The more the mass increases, the more the acceleration decreases. Now, let's think real life. Here, well, first of all, the fact is the acceleration is going to decrease. And we call that an inverse relationship. Inverse. Opposite. Okay? What that means, the acceleration increases, the mass increases, the acceleration decreases on the same side. One variable is going up, causes another variable to go down. All right, let's see that in real life. A truck with a load accelerates more slowly than a truck without a load. So here's the same force, the same engine with a lot of mass. Okay, now what happens if it doesn't have the load? It can go faster. It can accelerate faster. I'm not talking about how fast it goes down the road. Remember, that's speed. We're talking about the acceleration, how fast it speeds up. Okay, that doesn't seem too hard, right? Now, this is just a reminder as we finish up from the first law. If there is no net unbalanced force on an object, the object does not accelerate. The first law says if you don't push on it, you don't change its motion. And that push must be unbalanced, of course, external. So if the force is 0, F equals ma, the mass is whatever the mass is, 0 equals mass times what? Yeah, 0. So really, the first law is a specific condition out of the second law. See what I told you earlier? When you get math, you understand it. We see the math. Oh, we understand. Oh, and therefore, if there's no force, there's no acceleration. That's the first law. Things at rest stay at rest unless you act on them with a force from the outside. That's unbalanced. If it's in motion, it'll continue in motion unless you do that. And the second law says specifically about that force, that the more force you put on an object, the more acceleration you're going to impose on that object. So do you understand how the first law is a specific case of 0, 0. Leave it alone, nothing happens. But if we do start pushing on the object, then we use the second law to figure out how much force and how much acceleration. The second law is our math law. It's where we do equations that are that hard. 6 equals 2 times 3. Although it's 6 equals 2 times x, you have to solve it by dividing both sides by 2. Wow. Okay, you can do that. I know you can. The third law will not have any math on it. So the only one of the three that has math is the second law. It's the one that measures how much force, how much acceleration. The first law says no change in force, no change in the motion. If you do push with force, you are going to change the motion. That's all it says. When you want to know how much, you have to go to the second law. All right, that is it for today.